Okay, so for those who want background, these are some of the texts that may be used. I took yesterday Daniel Bowen's lectures out because they're fairly advanced, but some of the stuff tomorrow about Newtonian versus slow moving gauge and so on, which I will just skip completely almost, may be read there if you want to do perturbations in GR for those interested in that and to understand it a bit better. But they are more advanced than the level that I think is appropriate for these talks. The nice pictures also about the cosmic microwave background are from old but still very relevant pages by Wayne Yu in Chicago. They have a website with nice pictures of the parameter dependence of the cosmic microwave background and so on. I'll show some of them, and it's multi-level. Some of it is quite advanced actually, and some of it very elementary on the popular level, the website. So I suggest for those who want to know the cosmic microwave background at almost any level, get it from there. And there is a readable, a bit old but still very relevant article by him and Joe Silk and Naori Sugiyama that you can find. It was like also a bit old, but just before the big results of the cosmic microwave background in the early 2000s. So this is late 90s, but still very relevant because it discusses the very basics of what is the cosmic microwave background. Fluctuations, not the spectrum. We'll talk about all that here, but I'm just giving the books. And there's also an intermediate level review by Ewan Dedelson. This is like a comprehensive book on large-scale structure, more large-scale structure, meaning distribution of galaxies and things like that, and galaxy formation in the universe, stuff tomorrow. And this is the same by John Peacock. And this is a book for those who want to understand the cosmic microwave background and in some detail. It has to be relativistic perturbation theory because it deals mainly with photon fluids, photon coupled with background. So, and this for galaxy formation and evolution in general. So this is like a complete review, Mo van den Bosch and White. Mo is a person, van den Bosch is another. And White is a third person, Simon White. They have a book that is quite comprehensive on galaxy evolution and physical cosmology in all aspects, really, almost. Basically, the standard text on structure formation in current lambda CDM sort of cosmologies. Meaning lambda and cold dark matter. Lambda is the cosmological constant. But yeah, it is also relevant for all dark matter, standard, so to speak, dark matter-based treatment cosmology with galaxies. You know, okay? So, as we said last week, we talked about the evolution of the expansion as a whole, and we treated galaxies as points. And we treated the large-scale distribution as homogeneous and isotropic. For last lectures, not last week, last lectures, before Tuesday, I mean, last week is before Tuesday. That's last week for us. And now we want to discuss the part from here, from the cosmic microwave background, which is like about 400,000 years after the beginning of the expansion, to today, and we want to see how these things actually form. We call it the perturbed universe because you do perturbations from the homogeneous fluid, and you start getting clumpy things that eventually some parts of it is the galaxies we see. And there's other stuff, like dark matter that seeds the potential well for these galaxies that we see. So we want to get from there, these are fluctuations. This is a temperature. When you look at the sky, you see the cosmic microwave background, and you see at temperatures. We'll see when we talk about what we mean by a temperature, exactly, of the cosmic microwave background. And this temperature changes from theta and phi angles on the sky. If you do some polar coordinates on the sky, you see that you can make a map like that. And you can make another one of galaxies that at least superficially looks like it has some similarities. Galaxies today, this is more or less a local survey, a two-mass survey in micron wave. So you want to get from there to here, from there to here. This is here, this is there. This is time. And maybe tomorrow, the second talk, if you are not too tired, I will stop anytime tomorrow when it's too much, so that we can have more discussion. We will see why this thing that I took up the web and is like 5-10 years old or something is already showing that there are problems, because it says the first stars are at 400 million years, and we're actually seeing huge galaxies. We think we're seeing huge galaxies at 300 million years, not the first stars. So already there's tension with this naive thing. What it is, nobody really knows. It's the mathematics, astrophysics, fundamental physics. So if we get to it tomorrow, we'll discuss it. Now, the big thing in gravity is that it clusters. As we said in the first talk, in the first few minutes of the first talk, on Saturday, galaxy is attractive and unshielded, meaning there's no positive and negative, and long range, not like a Yucaro coupling. It's like an electromagnetic coupling, but with no shielding, with no positive and negative, only attractive. Okay, so it wins on large scales, and it makes things cluster, and if there's nothing to prevent it from collapsing, it will collapse into black holes. Okay? There's usually something to prevent it on the scales of galaxies, at least, and planets and most stars when they're alive and so on. Okay, what is this, the most usual something that prevents it? If it's made of gaseous pressure. Okay. So a normal sound wave is really a propagation of pressure. You talk, or you have a speaker, it vibrates, it compresses the air decompresses, it pushes the air next to it, which compresses, it decompresses, compresses, you have a propagating wave, like that. Okay? With gravity, if you compress, there's also a gravitational attraction within the compression. This becomes denser and it starts having gravitational potential energy. And if you remember when we talked about the air in the room, when we did our GM squared over R more or less equal to mv squared, we said there will be a scale R, and there will be scale R where m that goes as R cubed over R that goes as R squared, where the gravity potential energy will be greater than the kinetic energy of the gas in the room, which is, somebody said 300 meters per second, which is more or less the case, which is the sound speed also. The random speed is more or less the sound speed. When that happens, you form structure. It collapses. The sound wave does not propagate anymore, it collapses. This is called a gene stream. Okay? For the gas in the room, you can calculate 300 squared on one side, and what is the mass exactly that makes these two more or less equal? The kinetic energy on the right-hand side, mv squared, and gm over r, gm squared over r, the m goes together, so it's really v squared more or less equal to gm over r. Okay, so when that happens, I'll show it again, okay? So, but we'll try to do it a bit more precisely. Let's say, now we're not in an expanding coordinates and universe and so on. We'll do it very simply without expansion. For those who were around for the talk on Monday afternoon, you saw this hydrodynamics equations. We also did viscosity, but viscosity is not important now so we assumed an Euler equation, not Navier-Stokes. What is an Euler equation is this one. But before that, there is a continuity equation. What is a continuity equation? It's a mass conservation equation. It says the change in density, I think Polarian coordinates, meaning normal grid, X, Y, and Z that is center, that is fixed in the room. That's an Ornerian spatial coordinate. And I take at a fixed volume here, at a fixed position, a volume that is very large, containing many molecules, and small compared to the room. You can do that because even a millimeter cube will contain really a lot of molecules. So I take the partial derivative, meaning I stand here and I check the change in density. It will be the flux of mass in and out. Just says the change in density by volume is the divergence or convergence of the mass through a box that I take. Out and in. Trivial. The second one is also, let's say, trivial or simple, if you want. It's Newton's law of motion written in the Lagrangian coordinates, following the motion of the particle fluid. Lagrangian derivative is the total derivative, not simply du by dt. This is u, there's a typo. Not simply du by dt, but partial, but also the du by dx and the dx by dt, the motion of the fluid part. So this is Newton's equation. This is total derivative du by dt, and this is the pressure force. Now remember we said that pressure forces in hydrodynamics are pressure differences. A gas canister, a movement of the gas, there's a pressure force on the walls of the ampulla, the gas canister, because the pressure inside is much more than the pressure outside. Otherwise there's no force and it's empty. That's why an empty canister is safe. It's hot, in fact. Okay, so it's a nabla P that is the force, not the pressure, okay? Not P itself. Other than the pressure, the relativistic equations and so on, that was P itself because it was a mass equivalent to gravity. That's a different thing than the nabla P, the force here. There's no mass equivalent here. This is all Newtonian. Okay? So, and you have the Poisson equation if there is gravity. This is like the Poisson equation in electrostatics, but you take the 4 pi epsilon downstairs, it's because of the unit, and you put G, okay, because you have gravity. But because Coulomb's law is similar to Newton's law, you get the same equation. Except, of course, as I said, you don't have the Debye shielding in a plasma, for example. You don't have positive and negative. This is just attractive. You can do what you probably do a lot in your undergraduate physics, you linear eyes, meaning I take a small perturbation and I get a harmonic oscillator. Okay? I take a small perturbation around something and I get quadratic terms that are a harmonic oscillator. This is no exception. The wave equation is like that. It's many oscillators, right? Propagating. So how do we do that? We take small perturbations around an average density because we want to get the waves. We want to get that. So sound is a small perturbation, okay, in the linear regime. And we take the equation and we بنطرح منهم الباكجراوند اللي هم بنحط الباكجراوند we subtract the background, which is when we put rho and p to their unperturbed values. And we get equations for delta P and delta rho. And we can have a relation between delta P and delta rho that is called the adiabatic sound speed. Because sound is a propagation of pressure waves, okay? Adiabatic sound speed, which is what we'll deal with the rest of the talk, is sound speed when there's simply volume compression. There's no other things. There's no particle addition or subtraction, there's no viscosity, friction, things like that. So this is that. Yeah, simply, it's a wave due to volume compression and decompression of the gas. In this case, okay, a normal gas, and this is the definition of the adiabatic sound speed. Okay, it's a pressure wave propagating. Right. So we get a wave equation for sound. This is a wave equation for the sound. And this is a sort of an equation of state in some way. It closes the hydrodynamic equations. You need an equation to close because we have two unknowns here, we need an equation to close the system of equation. And this is the adiabatic sound speed. Okay? We put it in that and we get a wave equation. Right? And we can try solutions, and you will always get solutions of this sort for your linearization. Okay? You will always find some exponential solution, at least when it's in this form. You will always find exponential solutions. So these are Fourier modes, basically. Okay? With frequency omega and wave number 2 pi over lambda, wavelength, lambda, 2 pi over lambda, k. And with, it's called the linear dispersion relation between W equals CSK, linear. Okay. So this is without gravity. This is just an equation. We took the gravitational term off. Okay. This is just to show you what a normal sound wave with a linear dispersion relation is. Okay. This is a wave equation. This is an important equation in mathematical physics. People should know it. This is the linear equations. This is solution of a wave, as opposed to a diffusion equation where you don't propagate as t, you propagate as square root of t, for example, in time and things like that, when those who do diffusion. Okay, so this is a ballistic equation with things propagating linear in time, a wave propagating. Okay, so as opposed to a diffusion equation or things like that. Okay. So what happens when I put gravity? The Poisson terms comes over here. Okay. So it's not only these guys now, it is this. And when I put my nice solution, this can become negative. So instead of my density propagating as a wave, here, it starts to blow up exponentially. Why? Because when this becomes negative, this becomes imaginary, and I times I is -1, and my solution blows up, right? Instead of having a sound speed, which is, this is oscillatory, you know that, right? This is by the Moivre theorem, this is sine and cosine, right? You get sine and cosine. Because the exponential goes away. If this is negative, what's the square root of a negative number? -1, I, right? I times I is how much? Okay, so what happens to my solution? It blows up, right? So it blows up at it blows up because this becomes real. And there's two solutions, one minus and one plus. The plus one blows up, okay? And that's important, right? So, therefore, my waves don't propagate, they collapse. There's no propagation, there's no sound. There's boom, 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 boom. They cut important stuff if you want to know anything about gravity. It happens at the gene scale. This is the gene's wave number. It's when these two terms, when this becomes 0, we take this on the other side, and this is the gene scale. The inverse of the gene scale, or 2 pi over the inverse, is the gene's wave number. Okay? So this is the gene's wave number. What does it say? If you remember from last time, square root g rho, 1 over square root g rho from the beginning of the lectures was the dynamical crossing time of a gravitational collapse. All of the Friedmann equations of our ball thrown up, of our collapsing ball, of the crossing time in the galaxy, is all square root 1 over square root g rho. So this is the gravitational crossing time, and this is sound speed. What does this say? It says that when the gravitational crossing time is less than the speed of sound crossing, you collapse. Because the pressure doesn't have time to prevent the collapse. That's what it says. This. It says as long as the time to collapse is very long compared to the time for pressure to push it back, then we're fine. We have a sound wave. If the pressure takes billions of years to propagate and the gravity takes a million, then you collapse and the pressure can't do it. That's what the gene's instability means. And It happens when the potential energy also is of the order of the kinetic energy, which, if you have a gas, is the order of the thermal motion. Right? So, and then you have the Jeans length is that, and this is the dynamical time we did in the first few minutes of the first time. Okay. So, the first idea that you get is this is how you form a galaxy. Okay? This is how you form things. Well, not really. This is maybe how you form stars. Not maybe. Almost certainly, this is how you form stars. But this is not the current model, at least, at all, of how you form galaxies. Not in this form. Not with a gas and thermal temperature collapsing at the gene scale. It turns out the gene scale will not be of the size of a galaxy anyway, but we'll get to it. Why? Because simply the universe was too hot. Meaning, this thing was too big for the gas. This thing was too big for a very long time. Well, not very long, but long, compared to the times we want. Okay, so it was hot. We had a hot Big Bang. How do we know that? Because we see thermal equilibrium. Thermal equilibrium means something was hot in the sense of things in it randomly distributed. We'll get to that, I hope we'll be able to say something useful about it. And this is a Planck spectrum, black body. And it is the most perfect Planck spectrum that you can do. You cannot do a better random black body, random photons, distribution of photons, better than this one in the lab. But this is not in the lab. This is observed by Kobe a long time ago, but still, up to now, I think the most precise measurement of the spectrum, not of the fluctuations, of course, not of the spectrum. But soon there will be much better ones. There's a couple of experiments going on, or planned. So it's at 2.725 Kelvin, and people got a Nobel Prize in 78. Engineers basically got a Nobel Prize for it, Panzias and Wilson, because they were trying to detect a very low background radio antenna. And they couldn't get rid of this small load at 3 Kelvin. And they even went up and they went to the pigeon stuff, and they tried, and they called every radio station New Jersey, the East Coast of the United States, and things like that. And they couldn't get rid of it, and peoples helped them interpret what was going on. There were people already in Princeton trying to detect that thing, but it was detected by chance. Cosmology at that time was not like now. It was mainly for, not taken too seriously to give lots of funding to detect the cosmic microwave background. Although it was predicted by quite a few people, Alpha, Herman, Gamow, and so on. It was predicted. Because, when you compress something completely, things obviously become very hot and random. Intuitively, at least. Obviously, or not is another question, but intuitively. And he got the Nobel Prize only a few years ago for this and many other things he did. And there was another Nobel Prize in 2006, if you like this kind of thing. I'm excited by Nobel Prizes. There was another one in 2006 for the discovery of the fluctuations. Before we get to the fluctuations, here is the spectrum. Now, this guy, the spectrum, frequency and intensity, is in thermal equilibrium. It's a black body, means it has temperature. And so to every thing of this type, there is a Planck formula for it, and you can fit it with a certain temperature. Uniquely. Every curve of these guys has a temperature. Good. High temperatures are in blue, as opposed to what you get in the weather report. Low temperatures are in the red, infrared, and so on. Okay? Right? A longer wavelength. It shifts to longer wavelength at low temperature. So, 3 Kelvin, you can measure it very precisely in EV. if you put k equals 0 and so on, k equals 1, Boltzmann constant, then you get 10 to the, about a few, 2.5 or something, 10 to the minus 4 eV. That's what 3 Kelvin is. You can use Stefan's law, Stefan-Boltzmann law, to find its energy density. Okay, the T to the 4 law, which relates the temperature of a black body to the energy density. And then you can count the number of photons. As famously you should know, there's something wrong with this thing. I think I didn't save changes I made last night. Okay, I was editing it. Oh, it's fine. Or Mahmoud took a long version. He'll be punched. Okay, anyway, it doesn't matter. It's very small changes. So famously, this thing has a cutoff e to the minus e over kt, a Boltzmann factor that cuts it off here. Because otherwise you get what they call the Rayleigh-Jeans catastrophe. The energy density of the black body diversion is the volume in frequency space, basically, which is the number of modes, which is proportional to volume in frequency space, which is a common divergence you always get when you do frequencies and wave numbers and things like that. Not always, but when you don't have something to suppress it, like this guy, for example, or something else. Right? So then we can, so the photons, most of them will have an energy of order kT, because after that they will be highly suppressed. They will, the Planck spectrum suppresses the E to the minus E over kT. When E increases, it suppresses this thing over there. Okay? And therefore, your typical, so to speak, photon will have this. In fact, it's 3 kT. What kT? For our purposes, kT. Okay, so we can count the number of photons, really, because we know the energy density, and we think the energy density per photon is like kT. And we know the temperature, okay? We know the temperature, and we know the energy density. We divide that by that, you get like something like 10 to the 9. Okay? 10 to the minus 4 over 10 to the 5 is like 10 to the 9. Okay? So, 10 to the minus 9, your version is 10 to the 9. So it's, you have 10 to the 9 cosmic microwave background photons per meter cubed in this room. Quite a lot of them. You know, you have 10 to the 9 of them. You just divide the energy density by the energy by the energy of a photon, you get the number of photons. Okay, nothing exotic in this, right? So you get 10 to the 9. Compare that you have in the universe like 1 proton, not in this room, but in the universe, 1 proton per meter cubed. So you have like 10 to the 9 photons per proton in the universe. And this is quite a large number. And it's much more also than the photons emitted by galaxies and stars and galaxies and things like that. Photons in the cosmic microwave are really a lot. Okay? And they dominate everything. That's why there's only secondary effects in the cosmic microwave background by the other photons that come. You know? Or are being absorbed on the way from there to here and so on. There's not much barriers that to absorb them. You know, protons and electrons, things like that are barriers. Okay, so there's not enough of these things on the way. There's only minor effects on things called Zergovich silence and Zergovich effect and things like that on the CMB. Otherwise, the CMB would come as it is. Come as it is from where? From the early unit. But before that, I just want to quickly, like we did GR in one slide, we can do statistical mechanics in half a slide. So just to get the notion of temperature, for those who have no idea what the temperature really is. For temperature, you need thermal equilibrium. We cannot define temperature, formally speaking, at least outside of thermal equilibrium. You can define effective temperatures, and temperature, if there is a local temperature, there is a local thermal equilibrium, as is assumed in hydrodynamics, usually, or fluid mechanics, but you can't define a temperature. So also, by the way, this is called the entropy, which is simply the number of photons into the line. This is like the entropy on Mars. Not including gravity, I'm thinking. Entropy including gravity could be different. This is entropy just of states. So it's dominated by the photons. Okay? Gravity is another story. Okay. Entropy is this, as they put it on Ludwig Boltzmann's tombstone, Albert Boltzmann. Okay? So what is it? This is some constant, and this is the number of possible states. Okay, what is the number of possible states? Let's say I throw a lot of dice. I can have this dice being 1, this being 2, this being 3, or the reverse, all possible combinations. And they may be red or blue, or big or small, some other properties than there being 4 and 5 and so on. There could be other properties, like there being red or big dots or smaller ones or things of this sort. All possible combinations of that is omega. Now that's a Boltzmann entropy. Now, suppose I had no idea what combinations there could be. Then 1 over omega is the probability. This is the number of states, the probability is 1 over omega, and all of them are equal. So the Boltzmann entropy is the number of possible states. It's also, if I am ignorant, then it measures my ignorance. Okay? And it will be minus here. My ignorance is a minus, because it will be 1 over omega. That's a probability. And then my ignorance is a minus, because 1 over omega log is minus. Okay. So my ignorance is a minus, the number of states is a plus. Now suppose that I know that when I throw these dice, they're all independent. They don't collide on their way down, or the collisions are not important, and so on. So I don't really care about the detailed combination. This one is this, and this one is that, when this one is this, and this is the correlations between all these things. I care only about how many are 2, how many are 1 and red, how many are 1 and not red, and so on. Or the reverse, the probability of these things. Okay? And these will be simply multiplication of probability, independent probability. Like the probability of getting a coin half is half, the probability of 2 coins is a quarter, if they're independent, and then an 8, and then 1 over 16, and so on. Now suppose also I don't care, physically speaking, for some reason I have some physical insight, I don't care if it is red or blue or big or small. Then the probability are simply 3, the probability of getting a 3 or a 6 or a 1 or a 2 and so on. I don't care about the reds. I'm integrated over that. In statistics, they say marginalized over it. And because I don't think they're important. And let's say I have no constraints at all, then this is simply 1/6 for these guys. 1/6, 1/6, 1/6. And it's, there's a chance of getting 1/6, okay? But it's not like that in statistical mechanics, because usually I know something. I think there is a total energy that is conserved, for example. And I think I know it, So this is the entropy, this is the entropy, like that, of this guy. This, you put this and that, you get that, and this is the differential. You normalize your probabilities to 1, if you were doing probabilities, and this gives you 0, of course, and then you put an addition constraint, this one, okay? And I assume the energy is additive. The 1s and 2s of the dices are not coupled. This is not true in gravity, which ruins this whole thing. So it's important that in gravity, this whole thing fails. That's why gravity is so complicated. You can get any galaxy you like, although there's no most probable states in the classical term, and and things like that. In gravity, this is not true because the potential is long range and only one side. It's not true in a plasma, but within the Debye length. After you go beyond the Debye length, you're fine. Okay? So you put this constraint, and then you find your Boltzmann factor for the solution of ds equals 0, maximization of this thing, under the constraints that they're independent energies, not coupled like in gravity, and additive, independent, and constant. Then you solve this together, you get this is how you get a Boltzmann factor. Okay? And then when you try to, then you can play with it, you can take a small change around this maximum we found, or minimum, it's minus here, depending what you like. Yeah, a small change around that and compare it with a reversal entropy change in a reversible process in the lab. And then you find that your beta is 1 over t. So t is only defined when you have a sort of a reversible process. Otherwise, you don't. This is, you know this, right? dq equals dst. dds. Thermodynamics. Right. So Boltzmann factor comes like that, and temperature is a notion of thermal equilibrium. Now, why is this important for us? Because we think we had this thermal equilibrium. How do we know? Because we see the Boltzmann factor, really. And the modes, the number of the Rayleigh Jeans modes and the Boltzmann factor. How do we see it? But we see it in the CMB. So we see that we have a thermal equilibrium. And it's intuitive also, because remember, thermal equilibrium works, the calculation for thermal distributions all works. Not only because the things are uncoupled, but because we don't know anything about the system and really don't care because it's random. So a system that is highly interacting will tend towards randomness, intuitively speaking. Okay? Or if in a black body, just because of the, in the cosmology, it's interaction here that used to exist between electrons and photons, for example. Really large number, huge number of random scattering between electron and photon. You expect that to produce a thermal equilibrium. In a black body in a box, in the lab, is with the walls. Lots of scattering off the walls and so on. And you put this thing with a hole, remember this thing? A box, black box with a hole outside. So this is the same. Okay? So now, if you keep on compressing, the temperature increases, of course, of your gas and of your photons, because h mu increases, because lambda 1 over mu decreases when you compress. Remember the redshift? This is blue shift when you go back. So it becomes hotter and hotter and hotter because you're blue shifting your radiation. Okay? There are many eras. GUT era meaning the very beginning, and then QCD era, transition, and then electroweak transition, all those stuff Professor Said was talking about are actually there and supposed to be there, at least some of them for sure there. We can see evidence of it. And some of them supposed to be there, like the GUT and so on. So all these things are a laboratory, which we won't talk about, at least this year, but is of some importance. But it's not really the importance now. The importance is much more now in subjects beyond the CMB because of the observations and projects and so on. But this stuff is also important. So we are gonna do the last transition that is of this type, and it's an example. It's a transition from ionized plasma to hydrogen atoms. There is a bit of helium and so on, which again, if somebody wants to discuss, probably won't have any time to discuss, but maybe at lunch or tomorrow or whatever, we can talk a bit about that. Okay? But we'll suppose it's hydrogen because most of the universe is hydrogen. Okay? So when does hydrogen ionize? Do you know this? Like that this is the ionization energy of hydrogen? Who knows that this is the ionization energy? Okay, so a few people know. If you give hydrogen this energy, it doesn't become hydrogen anymore, it becomes one proton and one electron. You have a hydrogen atom, you shoot it with a photon of this energy, it falls apart and becomes one proton and one electron. So, when the temperature goes down beyond this 13 eV, if we're using natural units, so K equals 1, and so K the Boltzmann constant we found in the last slide. K comes from these things. See? When you compare these two, K is already in the assumption upstairs, but it comes here with the beta. Okay? So we can measure K. We know it fairly well. It's one of the fundamental constants. We put it K equals 1 here. So when this decreases beyond K equals 1, this becomes very large, the exponential, right? So e to the minus very large is very small. There's no more ionizing photons. They are suppressed exponentially. I don't have photons that can destroy my hydrogen atoms and create protons and electrons out of individual. So, but this, so intuitively speaking, you say, okay, so when T equals 13.6 eV, everything is gone, and I have the plasma is gone, and I have neutral hydrogen. It's actually a bit after that, a lot after that, because the E photon is 3T, 3kT, not 1 like we did in our order of magnitude. It's about 3. And then you divide by 4.5. And then there is 10 to the 9 photons per electron and proton. So there are so many of them. So I need that to be suppressed, not this, that. Right? And this is the recombination temperature. Of course, this is very approximate, subtle recombination. Order of magnitude things are more complex than that, obviously. But this is just to get the feel of how things are going. Right? And you need that to be less than 1, because there's 10 to the 9 of them. You find that this gives you 4.5, which is 3.6 over 3, over then, or natural log of 10 to the 9, gives you 0.2 eV. You can try this at home. Okay? So, a real calculation doesn't give you much different, by the way, on recombination. A reasonably real calculation gives you like around 0.3, okay, to one significant, to a rounding of this digit here. So that's about 3,000 Kelvin. So it means that the cosmic microwave background has expanded about 1,000 times from our 3 Kelvin of today to a recombination. Very important number. Because when you compress, mu increases because lambda decreases, so the energy increases, so the temperature increases. Okay? So the temperature is a linear function of the scale factor. So you can calculate the scale factor. Recombination is like a proper calculation gives you approximately, well, an approximate proper calculation gives you approximately 1100. So the scale factor at recombination to now is like 1,000. A very important number. This is a scale factor. And if you do an Einstein de Sitter universe, which is simply matter dominated from then to here, which is not a very bad approximation, because the CMB is really after matter radiation equality. There was an exercise here that you could calculate matter, when is matter radiation equality. If you given that radiation density increases like 1 over a to the 4 because of the redshifting, and matter density 1 over a to the 3. You'll find that it's about 10,000 Kelvin rather than a few thousand. It's earlier. So therefore, the CMB last scattering, this is sometimes called also the last scattering, but the last scattering is more precise. This is the recombination. Is mainly matter dominated, and dark energy only comes at redshift 1 or something. And this is redshift 1000. So the vast majority of time, you are in the standard lambda CDM, you are standard CDM, which is Einstein. This is a matter-dominated, and you can solve the Friedman equation. We did it last week, and you get that. So if you do that, you'll find that the cosmic microwave background recombined came when the atoms recombined 400,000 years ago. When they recombine, you don't have scattering anymore. It's Thomson scattering, by the way. It's non-relativistic because the temperature here is 0.2 eV or 0.3, and an electron rest mass is MeV. So the scattering between the electrons and the photons is non-relativistic. Okay? So it's Thomson scattering. So you can look it up if you don't know. Thomson scattering, just scattering, classical scattering, electrons and photons. Okay? And then a photon comes with an electron, and it has a wave oscillating. It exacts the electron basically. It makes it oscillate like a harmonic oscillator. So for a limited time. So it gives it energy. Okay? So, and then it passes. Okay? So that's Thomson scattering. So you get about 400,000 years, which is not a very bad approximation of what actually happens. Okay? Now, this is for the CMB spectrum. Now, what about the fluctuations? Now, we know now how to measure the temperature with Planck spectrums. And we know the temperature. We know there's thermal equilibrium, there is a temperature, there's a Planck spectrum, we can measure it very precisely. And we can measure it from place to place on the sky, and we find this color-coded, of course, it's not, we don't find a fireball. We find, different temperatures, and they color-coded like that to show it's a fireball, and so on. But there are other ways of color coding, obviously. And then they are of order delta T over T, 10 to the minus 5, very small, but very important. Because if they don't exist at all, nothing will happen. You won't get galaxies, stars, and planets and things. So the calculation of that involves quite complex kinetics with coupled photon baryon fluid, electrons on a gravitational background, but the basic physics is extremely well understood, or at least fairly well understood, at least compared to the complex galaxy formation that we should discuss tomorrow if time permits. So, what is well understood? Pressure, radiation, as we said last week, has, beginning of the week, has pressure. Third E or third row gamma, as written here. Okay. This is radiation pressure. Important in astrophysics, also in stars, massive stars, for example, and AGNs and so on, not active galactic nuclei, not only in cosmology. So we put C equals 1. Natural units. And the rho gamma is T to the 4. And there are density n cubed, T cubed of electrons, and another T for the energy of the electron. That's redshifts and blue shifts and so on. So it's T to the, so the density is T cubed. We observe this thing, we plot over theta and phi coordinates. We make a map of T at something minus the T average. We take the average over all this thing, and we divide by the average so that we can get a relative fluctuation. This is what is more or less 10 to the minus 1. 1 part of the wahda ala 100,000. And because of these relations here, and assuming that all fluctuations are adiabatic, meaning volume compressions, in the relativistic terms of the metric, volume compressions that like our adiabatic gas, we looked at it, so to speak. So there are these relations. This comes from the fact that this is T cubed for the matter, and this is for the gamma T to the 4. It's quite elementary, you should be able to do it. Now, forget about the matter for now, and let's take only the photons. Why? Because we will try to be studying sound waves from in a baryon photon fluid. Baryon, not all matter. Sound waves are in the baryon fluid. The dark matter, does not contribute to the waves because it doesn't have pressure, it doesn't have electromagnetic interactions. Okay, at least in the standard CDM or something. So it doesn't have, it's pressureless by the time you come to this stage. It should, because otherwise you wouldn't be solving the problems you would be talking. Okay? So it's non-relativistic and it's slow and so on, it doesn't have pressure. What has pressure is the baryons and the photons. But the baryons up to the CMB are much less than the photons. Their energy is less. Even though equality happened before, but the baryons are fixed if there is dark matter. And also, for before that, the whole universe was very heavily radiation going. So at the zero order approximation, we want to do sound waves of a photon fluid. Why do we want to do sound waves of photon fluid? First of all, if there are perturbations, there will be sound waves when there is pressure. If it doesn't cluster to ground. And photons are unlikely to easily cluster because they're moving at the speed of light, and the speed of sound is this. C squared is this. So C of sound of photons is 1 over square root of 3. So the sound speed is so big that the Jeans length must be big. And the Jeans length was the competition between the gravitational time and the sound time. And the sound time is quite efficient because it's almost the speed of light. So you won't have much clustering in the photons. So there will be sound waves. So let's say they're pure sound photon sound wave. No gravity, nothing. Just to get an idea of what's going on. So we have a sound equation, except it's now written in conformal time. This all technical stuff, but take it as the sound equation that we looked at when we put 4 pi g here as 0. The one we solved with sines and cosines, e to the power of I, and so on. And take omega out because we're looking at a given time, but do Fourier, we do the Fourier analysis. For our purposes, the Fourier analysis for now is doing the stuff in space. Yes. This is Fourier analysis for our purpose. We do a solution of this stuff. The Fourier analyze it into waves. Right? There we go. So this is our wave equation for the photon fluid. Okay? That has pressure like that. It has a continuity equation, of course. There's a slide in the very back of the talk, so if you want to see how this is done in some detail. So if you're interested, look at it. I'll try to make it organized also. There's lots of material at the end of the talk if you want to go through these things in a bit more detail. Okay? But let's take it at face value. We just replace this by this, and this is our temperature variation. And for the adiabatic volume compression initial condition, the initial theta naught is small. Theta naught is small. Because simply volume compression, there's nothing moving, there's no flow. Okay? So this is my solution. It's not sines and cosines, it's only cosines. This is my solution. Okay? Where CS is the square root of this, it's square root of 3. C, of course. I'm using here C equals 1. And this is the conformal time that we did in the first lecture. The C equals 1 this time, so it's really a time, not a space, so to speak. That's, in theory, people use that. Okay? So it appears like a time, it's still a distance. Okay? So we did that, supposedly on Monday, I think, or something like that. Okay? Okay, so what do we get? First of all, how do we observe these sound waves? We don't see them when you have a map that is like that. You don't see sound waves here. You see just a lot of really apparently completely random positive and negative delta t. So the way we do it, the way people do it in these things is they take something called spherical harmonics. As you do in Fourier space with translation and variance, over the sky, you can do spherical harmonics for rotation. You probably met them in the hydrogen atom. You can solve the Schrodinger equation for the spherical potential in spherical harmonics because of the symmetry. Okay, but we don't use them here for solving anything. We use them to, as the Fourier analyzes things into spatial scales, this thing analyzes them into angles, theta and phi. And you can take theta and phi and square it and so on, and you get a power spectrum with an angular scale. These are called multipoles, N, like of the hydrogen atom, more states. But this is different, this is not state, this is data analysis. So you can see that the powerful methods that are useful theoretically can be useful in data analysis and engineering and many things. These are important things. Fourier analysis, psychoharmonic, Bessel functions, and what have you. So it's not simply to understand really deep things. It's also even to do data analysis to understand the deep things. So it's all without this basis of what's called the Sturm-Liouville theorem, these sorts of functions, things are not clear. Hilbert spaces, of course, are examples also. Linear functional spaces are sometimes spanned by these things as in the hydrogen atom. So, okay. Right, so you take it at different scales. You want to see big scales, small scales, like the Fourier, but in angles. Big angular scale, small u. تمسحها. This is what this picture. Okay? So, and you see peaks. These are squared, okay? It's a power spectrum, so this is squared. What do these peaks correspond? Now, when are we seeing the microwave background? We're seeing it, we said, at about 400,000 years. So we don't have time evolution. We have a snapshot at a given time. When the electrons and protons recombine to form atoms, and then they were much less free to come to us. And because there's so many of them compared to stars and galaxies and so on, they come fairly free. They come, not completely, but to a large extent. Okay? Other things. So, when do you see peaks in the cosines? You see it at n pi, right? There's a maximum and minimum every pi. One maximum, then, well, there is half an oscillation at every pi. And so, in the square, you'll see peaks at every pi. Okay? Because it's half an oscillation, half a lambda, half a wavelength. Okay? So, the first peak, if we are correct, will be the first compression, the second peak, the first verification of our sound wave, and the third peak will be a second compression, and so on. Now, okay, so first compression until what? The peaks here will be the first compression that is happening just as we're taking the picture, the snapshot, at recombination, 400,000 years, or about. Last category, okay? About. Right? So these are the waves that have their first, there's all sorts of waves. This is a continuum of waves. We have free boundary conditions. There's all sorts of supercake, can be anything. Of all these anythings, there is one of them that's making the first compression. And there's one of them that's making the first verification. And there's one of them that's making the second compression. And so on, right? Of all the possible waves, there must be one doing that and doing this, and things like that. So these are the peaks. Okay? A few things. After that, there is damping. Diffusion damping. It has many reasons. One of them is there are many oscillations. And you hear the modes that are the bass. Another one, when you near the last scattering, the mean free path becomes very large, and those who did the lecture on Monday know that the mean free path is connected to the viscosity, much more viscosity than this mean free path. Okay, those who did the hydrodynamic turbulence and so on. So viscosity starts becoming important, which is completely ignored So it's not cosine waves, it's viscosity. And there's other effects. We're only considering here the temperature variations due to the compression, but there's other effects. There's something called the Sarsouif effect, which is due to the photons escaping the potential wells, redshifting of the light. It's a relativistic effect. When the light leaves a potential well, it redshifts. So this should be also included. We're not including that. We're only including the compression. And there's Doppler effects because there's movement of the gas. Photon gas and baryons and so on, so there's that. And there's a few effects we'll talk about. So the emission effects are all of these. So it's a fairly complicated thing. But let's say we can understand the basics, and we do. Well, how do I know that we do? Because we can actually calculate the angle from our cosmology. So, peaks of co-moving size d will have size r times theta. And now we need an r. The angle times the Euclidean distance, r, is the size of the thing. So do we know the size of anything? Yes, we do. Because we're saying the first peak, for example, is the sound horizon that is making the first compression during a sound travel time from the beginning of the expansion to the recombination, 400,000 years or so. So we think we know something about that. So we know a bit this sound horizon. It's the sound speed time, the co-moving sound horizon is the co-moving distance. Sound speed is the sound speed integrated over the co-moving distance, okay, d tau, which is, if we assume it's a photon fluid, it would be that. Okay, tau would be tau star, which would be co-moving time, conformal time, sorry, up to the recombination over square root of 3. Light moves S star, sound in a photon fluid moves tau star over square root of 3. Light moves tau star, sound in a photon fluid moves tau star over square root of 3. So we think we know that. Okay? Here it is. So D is half the peak because a full cosine wave is compression and rarefication. Half of it, half lambda peak, should be S star over the n, the number of compression and rarefication. So for the sound horizon, the first peak, the one here, it's 1. So it's simply half the lambda of the peak. So we think we know D of the sound horizon. How do we know it? From simple physical arguments about how much the sound in a photon fluid moved during the time, from the beginning, so to speak, expansion, through the recombination. It's simply the light co-moving time over square root of 3. Okay? And the light co-moving time, we can calculate it also. So, but we don't need to because it's very small compared to the distance now. Okay? And you can do much better than that. You can calculate, of course, this with a photon fluid coupled with the baryons, and you can do the kinetics. You don't need to make this very rough approximation of a complete photon fluid that moves at 1 over square root of 3, with waves that move 1 over square root of 3, the speed of light. Okay? So then we can calculate theta, d over r. And maybe we can try a flat universe to calculate that. Okay? So we have r to the recombination, which is our r here. We are looking at the CMB at z equals 1,000 or a equals 1 over 1,000, and we are here. And this is our Friedmann coordinate, which from talks on Monday is the co-moving distance, which is a difference between the co-moving time now, or sorry, the conformal time now, and the conformal time at recombination. And because the conformal time now is much larger than the conformal time at recombination, because the time itself is much larger, obviously, 400,000 years or 14 billion or whatever, as we calculated last time. So it's equal more or less to the conformal time now. So the conformal time now. So theta, therefore, from this, d over r, will be tau squared to recombination over the conformal time to recombination over the conformal time now. Okay? All the way over 1 square root of 3, which is the sound speed of a photon fluid. And this ratio here for matter domination is a to the half. Okay? We will assume again an Einstein de Sitter universe made of matter domination. Okay? And so, and we know that A star over A naught is 1/1000 from the recombination calculation we did over here. Okay? We know that the scale factor, the temperature of this 3B was about 3000 at recombination, and it's about 3 degrees Kelvin now. So it's a scale factor of 1000. So therefore, A recombination over A now is like 1/1000. And this is the relation between the conformal time and A. How do we get that if we put out? Then we put A T proportional to T over 2 over 3. That's an Einstein's matter relation. We say that the universe since the CMB to now was completely matter-dominated flat universe. Okay? No lambda and no radiation. Okay? It's a good it's not a bad approximation. Okay? So this is how we know that A is proportional to tau squared by putting A proportional to T to 2 over 3 here. Okay? Then you get tau proportional to A to the half. Okay? And you know A star over A naught, so you can calculate it. Doing that, you can get theta from this, and you can find it 1 degree for the sound horizon for the first beat. Okay? So therefore, and it is, we took the map and analyzed it into multiples, right? Into the spherical harmonic part, into the multiples. Well, only the multiples here, because average over theta and phi, the spherical harmonics. And and that divides it into angular scales, like the Fourier modes divide into spatial scales. The multiples divide into analyze into angular scales. And we find that our peak is approximately at 1. That tells you that we are more or less in a flat universe. Because a rough calculation of the expectation of theta, given R theoretically calculated from a flat universe, gave 1 degree. Now what happens if we curve things? These peaks move when you curve the universe. Because the FRW coordinate R is not archi anymore, like in a flat universe. R is sine archi. Okay? It's not R anymore, it's R sine archi. So this is smaller. So things appear larger. So in a curved universe, this will not be 1 degree. It will be 1.5 if the curvature is very large. In a positive universe. In a negatively curved universe, it will be like that. It will start moving this way. Okay? Starts moving to higher multipole, smaller angles. Things will appear further, so to speak, for a given cone universe. Because the sign here is replaced by a shine. Okay, for a hyperbolic spatial universe instead of a flat. Right? Let's go to that. So things will appear further. This is another effect that it's called the integrated Sass-Wolff effect. different story, okay? Now, when you put lambda, things will also appear early because of the accelerated expansion. Here, we didn't put lambda at all. We just assumed the Einstein de Sitter universe flat with A proportional to T to the power 2 over 3. But if you put lambda, things are a bit further. So the 1 degree will go this way to become, let's say, 0.99. The effect of lambda is not very big of the dark energy because it only comes later. It comes at z equals 1 or something, and we are going from z1000 to z0, so the dark energy comes only later, so the effect is not as big as the curvature, for example, which has a relatively large effect. It's there. Okay, so to recap quickly, we said that something of size d will appear at angle theta at distance, Euclidean distance, FYW coordinate r. We said that we could know d of the first peak from the sound horizon, the first compression. And because we know d at the first peak, we can theoretically calculate r to see what theta we get. So we theoretically calculated r in a flat universe. It's the difference between the conformal time now and the comoving distance. It's the difference between the conformal time now and the conformal time of last scattering, which is about the conformal time now. We use the formula for theta taught in Auline D, and so this is the angular diameter distance, and we get theta from the angular diameter distance comoving here. And so we get the ratio of the two, which we know if we assume a theory, a dynamics, like we did with the supernova. So we assume a theory. Our theory is a to the power a proportional to 2t to the power of 2 over 3, which gives you, when we know that because of the ionization of hydrogen, which gives you the theta equals more or less what we observe. So our universe is not too far from a flat, at least with this naive calculation, from a flat, matter-dominated, later matter-dominated, Einstein de Sitter universe. And then, in the very late stages, you can find the cosmological constant from here, by fitting. Okay? And that's what lambda CDM is in terms of the cosmic microwave diagram. And then you can get a value for H naught, the Hubble constant. Because suppose I know these things from the supernova or from whatever, our omega r and which radiation. The radiation I know already from the CMB itself, how much it is. Suppose I know omega lambda and omega m independent. Let's say as we did on Monday from the supernova. Then, and I know this from z1000 to z now. I know also the integrals from where to where. Then this is completely fixed. And this is fixed by the angular scale that I just calculated. I just figured it's fixed from observations. Completely fixed. There's nothing I can do. So there is an H naught. I can calculate the value of the Hubble parameter right now. Remember this from Monday, this was the Hubble sphere. We multiplied the Hubble sphere for this integral, for the supernova, remember? Anybody remember the Hubble sphere? So this is the Hubble sphere, completely fixed. If I know omega n and lambda and so on, I fix the Hubble sphere. So, and it comes with a different value than the Hubble sphere from the supernova. Slightly different, at least compared to when I use your H, it was like 50 and 100. The differences between the different estimates. Now it's between 67 and 73. So 68 and 70 something. So difference is not that large, but it's becoming cliche for a quarter of a century that we are in the age of precision cosmology. So now I said that we could determine these guys from the supernova, but we can determine it also from the CMB itself. Okay. Why? Because we completely ignored gravity in our equation up to now, but indeed gravity does have an effect. You know, it's not like you're going to have a collapse of the gene scale, but you know, the self-gravity of the waves does have an effect. And it has more of an effect, so we call this, it becomes a harmonic oscillator or something with M effective instead of massless. Okay? So it's a correction. And it's there even for a photon fluid, but we ignore it. But if we want to know the effect of baryons, meaning protons and electrons, well, normal, I mean by that, normal matter. Okay? Protons mainly for this thing. So, and then there is an M effect, okay? That makes the waves not, first of all, the waves don't propagate as fast. You can do this very simple calculation that when you include now the pressure is only of the photons, because the photons are relativistic. The electrons and protons, as we said, are not relativistic at all. It's a pressure only of the photons, but the mass is of the protons and the photons. So the sound speed decreases. Yeah, because you only have one component that's doing pressure, and you added another one that's not doing pressure. Okay? So the sound speed decreases, and the self-gravity becomes more important when you add the protons, and so on, and the rest of the stuff. Okay, so therefore what happens? It's like, they call it mass loading. You load the compressions becomes bigger than the replication. And the gene scales بالضغط خالص ما بيقومش خالص هنا بيقوم بس أضعف. And therefore there is an increase of the ratio of the compression to the rarefication of the first peak ratio to the second. And you can calculate that quite precisely with those components. So there's an increase of the first peak, the compression, compared to the second peak, rarefication. بالضغط بيقوم أصعب because of the effect of including gravity and including gravity of the values of the protons. So this is one effect. From that, you can measure the baryon fraction, 5%, how much baryon. You can measure the dark matter fraction from something called decay and radiation driving. The dark matter were not participating in this business of the waves at all. They make the potential healthy and more or less stable. In an Einstein-de-Sitter universe, if we have time, we can show it tomorrow, meaning flat, matter-dominated, these potential wells stay the same because the density grows in a way that cancels the expansion of the potential wells are constant, at least in the linear region. So linear meaning fairly small direction, which we are in 10 to the minus 5. Okay? But if there's not enough dark matter, the potential wells will just expand away. If the universe has much more radiation, radiation quality happens much later. The universe has much more radiation. Let's say it has very little dark matter and only has baryons, then we're radiation dominated all the way to the CMB. And when the radiation domination happens, it means the universe is expanding much faster than the potential wells of the dark matter can make up for. And the potential wells start decaying. And this is a measure of how much dark matter we have. If we almost have no dark matter, there will be no potential well, almost. So the height of these peaks, and especially these guys that get the second and third verification that get, washed away, is a measure of the dark matter. The height of the peaks is a measure of the dark matter, especially the third peak. Okay? And this is much bigger evidence for dark matter than the rotation curve, by far. It's very precise. You cannot get away from it. It's percent things, and very difficult to do modified gravity. Some people try, but it's not easy. huge problems to modify general relativity or Newtonian mechanics or here general relativity to do. You can modify GR and Newtonian mechanics well and maybe do almost as well or even better than dark matter in galaxies. But you cannot do it here easily at all, and the dark matter fits perfectly. So this is the main evidence for dark matter. Take that home with you, okay? But the non warranty funding. Okay? So, curvature, dark energy. This is the integrated Sachs-Wolf effect. Is an interesting effect. معلش بس هو اللي الدكتور سيد. انت قدامك اهو. ماشي احنا الاثنين انا وهو. انا وهو. احنا الاثنين. لا ما انا برضه اتاخرت اتغير يعني. Okay, so integrating Sachs-Wolf effects just very quickly are things that are called secondary effects on the microwave background. One of them I mentioned, sometimes the Goldwich effect, which is like that. When the cosmic microwave background meets galaxy clusters, it gets, which have relativistic electrons, it gets boosted. Its frequency goes from the microwave to visible. Inverse Compton boosting. So that's one of them. There's lensing. The microwave background, when it comes to us, it is lensed by all the intervening matter. And that's an important probe of what's going on. Right? And the microwave background is lensed. When it comes from the last scattering surface of the combination here, it passes through galaxies and clusters and large-scale structures and all, so it is lensed. And there is the integrated Sachs-Wolf effect. It also redshifts and when it comes out of potentials. Group shifts coming in, redshifts coming out. So that's another effect. This effect is not there at all for a completely matter-dominated universe. Because as I said, the increase in the potential wells makes up for the expansion. So you in a linear regime that is probed by the CMB, so you don't see anything at all. Okay? Or much less. But for a universe with dark energy, it is important. Okay? Because the potential wells start, like in the radiation era, changing with time. And changing dark energy, it is a very big test of the dark energy. But that's another story. So, we can measure curvature by fitting this thing, and this is the lambda CDM. That's why this is the most perfect thing for CDM and lambda. As you can see, the fit. This is the theory of the lambda CDM, and this is. So the CMB is evidence for dark matter. You cannot do it without dark matter at all. If you put modified gravity, you can, but at a very high price. Within GR, you can't. No way. Close. With a modified gravity, a very, very complicated high price, you may be able. But then you probably will mess up all the things. So, by changing the dark energy, the curvature, the variance in the matter, we can fit that. And what do we get? We get the parameters, 70% dark energy, 25% dark matter, 5% variance, and so on. And we get H0, don't forget that. And they come more or less like the supernova data, but with something called H0 tension that arose in the last few years. Okay? So that's it for this talk, that's more than enough. Okay? I guess maybe questions at lunchtime after if you have any questions after كم على طول ولا تعبانين؟